Good. Well, let's pray and we'll get started. Father, thank you for today, and thank you for science and how you've helped us to understand the world around us through these things and know something of your mind in creation and upholding the universe. Help me today as I teach this last section on the ideal gas law, and help the students to really learn these things and retain them, and to really just excel on the midterm coming up. Praise you, Jesus' name. Amen. So just a reminder, the midterm will open tomorrow-ish, or I guess the next day-ish. I got to get it written and uploaded, but you'll have like through the 16th to get it done. So plenty of time to do it. All right, where were we?
Sample problem 9.21.
Nice, thank you, sir. So we're doing sample problem 9.21. Okay. This one says, it takes 243 seconds for 4.46 times 10 to the negative fifth mole of xenon to effuse through a tiny hole. Under the same conditions, how long will it take for 4.46 times 10 to the negative fifth moles of neon to effuse? Okay, so my head's not been in this for a minute. But we have Graham's law, right? So Graham's law says rate of effusion for xenon over the rate for neon is equal to the inverse of the molar mass of neon over the molar mass of xenon, right?
Yeah.
So I can use this and I can go, all right, my rate for xenon is 243 seconds for xenon. We're trying to solve for neon, and it's equal to the inverse of their molar masses. So what's my molar mass for xenon?
Do we need to multiply it to the...
Oh, yeah, we're not. You are right about that. Go ahead and give me your molar mass here.
Okay.
What do we have for molar mass for xenon?
131.29.
131.29. Okay, grams per mole. And how much for neon?
It's 20.179.
20.18 grams per mole. Okay. Now, as you were pointing out over here, I need to calculate the amount by time to come up with my rate. So I need 4.46 times 10 to the negative fifth moles, right? And over here, I'm going to have the exact same amount, right? Okay. So I'm going to cross multiply and divide, and that's going to give me a rate, and then I will go from here to determine the rest, right? look right to you so far? Just wondering if you got the same numbers. I guess I'll know in a moment. Victory. You get a little in the weed. This calculator doesn't do scientific notation too well.
Yeah.
And even to do square roots, I'm having to like put things in parentheses, and so I'm always like, man, I could have had a bad keystroke, and this would be so off. But all right, so just to explain how we got here, rate equals moles per second, right? So we know this when 4.46 times 10 to the negative fifth over a rate of 243 seconds. We were given that. I went ahead and I did that math. It puts me at 1.84 times 10 to the negative seventh moles per second. And that rate divided by the rate for neon, which I don't know. I know the number of moles, but I'm ultimately trying to solve for the number of seconds, is equal to the inverse of the square root of the molar mass of neon over the molar mass of xenon. And so I transplant that all over here. I multiply this times this, divide by this. That gives me what this equals. So I have my 4.46 times 10 to the negative fifth over my seconds of neon. That was the number here. I multiply this times this. I didn't do it, but that's how we do it, right? To get this out of the way. And then what I want to do then is divide this by this, right? And so I get moles over seconds equals rate, right? But I want to solve for seconds, so I multiply that, and I go moles equals seconds times rate, and then I divide everything by rate, so I get moles over rate equals seconds, and when I do the math, I get 95.30 seconds. And I realize I'm not always good about talking through my steps. That could improve. Let's take on the next one. That was a lot of work for one little problem.
Yeah.
All right, well, here we go. A party, do we want to do all this? Do we have time to do all this? We're going to skip the next one. We're going to move on to 9.22. Okay, we're skipping the check your learning one just for time. The answer is there if you want to do it. So example 9.22, determining molar mass using Graham's law. An unknown gas effuses at a rate 1.6, so gas X we're going to call it, has an effusion rate of 1.66 times the rate of CO2. Okay? What is the molar mass of the unknown gas? Can you make a reasonable guess as to its identity? So, the the rate of fusion, we said, is equal to 10 times the rate of CO2. That means 10 times faster, 10 times more rapidly, 10 times faster. Okay. So it's actually, what is it? It's going to be CO2 divided by 10 over CO2 equals molar mass of CO2 over the molar mass of X. Does it seem right to you? Mm-hmm. Okay. This is rate. This is rate. Okay, so we need the rate of CO2. Mm-hmm. What do you got?
Well, I have 12.
Where did I get 10 from? I don't know how I came up with the number 10. It should be 1.66. An unknown gas diffuses at a rate 1.66 times more rapidly, right? Mm-hmm. Okay. So we need the rate of diffusion for CO2. Are we given that in a chart or anything?
No, I don't have it.
Okay. Well, let's see how we're supposed to come up with this real quick. We don't even need to know. We don't even need to know it. We can cross out the CO2 and put a 1 for it, right? Mm-hmm. So we can take the same thing and we go, all right, 1.66 over 1 equals molar mass of CO2 over the molar mass of X. Okay. So we go, let's go ahead and let's do that, which means I'm going to cross multiply and divide, right? So I'm going to get molar mass of CO2 times 1 divided by 1.66. It's going to give me my molar mass of X. All right? Yeah. Molar mass of CO2 is
44.011.
44.01 square rooted over 1.66 equals the square root of m sub x. So let's go ahead and do that. I get 3.996, so I'm going to go 4.00 equals square root of m sub x. Right? Okay.
You need to square each side.
So 16 equals x. Okay. Yeah. So what gas is going to have an approximate molar mass of 16?
Oxygen?
No, it's not going to be oxygen.
Because oxygen will be 32.
It'll be 32. It's going to have to be low, right? You're probably looking at nitrogen, carbon, oxygen, chlorine, right? Or not chlorine, fluorine. If it was fluorine, you'd be looking at something like 9, right? 9's not 16. If it were water, right, it would be 18. That doesn't work. If it were carbon, you'd have 12. You could do CH4, right?
Yeah.
Which would get you 12 plus 4 would be 16, so that works. If you had NH3, you'd be looking at 17, right? Is that right?
Yeah.
That didn't work. Okay, so it's got to be
CH4.
CH4, which is what it is. All right. Nothing too hard about that one, was there? Let's go ahead here. I got to erase it. Sorry about that. Kinetic molecular theory. This is section 9.5. Okay, kinetic molecular theory. The gas laws that we have seen to this point, as well as the ideal gas equation, are empirical. That is, they have been derived from experimental observations. The mathematical forms of these laws closely describe the macroscopic behavior of most gases at pressures less than about 1 to 2 atmospheres. Although the gas laws describe relationships that have been verified by many experiments, they do not tell us why gases follow these relationships. The kinetic molecular theory is a simple microscopic model that effectively explains the gas laws described in the previous modules. This theory is based on the following 5 postulates described here. The term molecule will be used to refer to individual chemical species that compose the gas. Although some gases are composed of atomic species, for example, the noble gases. So, number 1, gases are composed of molecules that are in continuous motion. Traveling in straight lines and changing direction only when they collide. Okay, so in straight lines, until collisions. Fair enough? Okay. Number 2, molecules composing the gas are negligibly small compared to the distances between them. Number 3, the pressure exerted by a gas in a container results from the collisions between the gas molecules and the container walls. Number 4, gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic and do not involve a loss of energy. 5, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. Okay. The test of the kinetic molecular theory and its postulates is its ability to explain and describe the behavior of a gas. Various gas laws can be derived from the assumptions of the kinetic molecular theory, which have led chemists to believe that the assumptions of the theory accurately represent the properties of gas molecules. We will first look at the individual gas laws, Boyle's, Charles's, Hamilton's, and Avogadro's, and Dalton's, conceptually to see how the KMT explains them. Then we will more carefully consider relationships between molecular masses, speeds, and kinetic energies with temperature and explain Graham's law. Okay. This is a lot. It's a lot of words. Recalling that gas pressure is exerted by rapidly moving gas molecules and depends directly on the number of molecules hitting a unit area of the wall per unit of time. We see that KMT, kinetic molecular theory, conceptually explains the behavior of a gas as follows. With Hamilton's law, the temperature is increased, as temperatures increase, the average speed and kinetic energy of the gas molecules increases. If the volume is held constant, the increased speed of the gas molecules results in more frequent and forceful collisions with the walls of the container, therefore increasing the pressure. Okay. Charles' law. If the temperature of a gas is increased, a constant pressure may be maintained only if the volume occupied by the gas increases. This will result in a greater average distance traveled by the molecules to reach the container walls, as well as increased wall surface area. These conditions will decrease both the frequency of molecule-to-wall collisions and the number of collisions per unit area, the combined effects of which balance the effect of the increased collision forces due to the greater kinetic energy as at the higher temperatures. For Boyle's law, if the gas volume of a given amount of gas at a given temperature is decreased, so as volume decreases, is that right? If the gas volume of a given amount of gas at a given temperature is decreased, that is, if the gas is compressed, the molecules will be exposed to decreased container wall area. Collisions with the container wall will therefore occur more frequently and the pressure exerted by the gas will increase. Avogadro's law. At constant pressure and temperature, the frequency and force of molecule-to-wall collisions are constant. Under such conditions, increasing the number of gaseous molecules will require a proportional increase in the container volume in order to yield a decrease in the number of collisions per unit area to compensate for the increased frequency of collisions. So, for pressure and temperature to stay the same, as the number of moles increases, then our volume must increase. Finally, Dalton's law. Because the large distances between them, the molecules of one gas in a mixture bombard the container's walls with the same frequency whether other gases are present or not. And the total pressure of a gas mixture equals the sum of the partial pressures of the individual gases. I'm not even writing that down. That was pretty self-evident. All right, here's where we're going with it. Looking at molecular speeds and kinetic energy. Previous discussions showed that kinetic molecular theory qualitatively explains the behaviors described by the various gas laws. The postulates of this theory may be applied in a more quantitative fashion to derive these individual laws. To do this, we must first look at speeds and kinetic energies of gas molecules and the temperature of a gas sample. If in a gas sample, individual molecules have widely varying speeds. However, because of the vast number of molecules and collisions involved, the molecular speed distribution and average speed are constant. This molecular speed distribution is known as the Maxwell-Boltzmann distribution. Let's write that one down. So Maxwell-Boltzmann what this is saying is that speed of molecules varies. But there's so many that the average is pretty consistent, right? In a gas sample, individual molecules have widely varying speeds. However, because of the vast number of molecules and collisions involved, the molecular speed distribution and average speed are constant. Depicts the relative numbers of molecules in a bulk sample of gas that possess a given speed. Okay, I'm going to now need to erase everything I just wrote so we can write a whole lot more. The kinetic energy of a particle of mass and speed is given by this formula. Ke equals 1/2 mu squared. So in this formula, this is kinetic energy. Equals 1/2 of, this is mass, and this is speed. Okay. Expressing mass in kilograms, and speed in meters per second, we yield energy values in units of joules. So that's useful to know. And we need to know that 1 joule equals a kilogram meter squared per second squared. Okay. All right. To deal with a large number of gas molecules, we use averages for both speed and kinetic energy in the KMT. The root mean squared speed of a particle is defined as the square root of the average of squares of the speeds with n equaling the number of particles. Okay. So the average root mean squared speed is equal to that, which is equal to clear as mud. Okay. All right. What are we doing with this? Root mean squared speed is defined as the square root of the average of the squares of the speeds with n, where n equals the number of particles. The average kinetic energy for a mole of particles then is equal to average kinetic energy for a mole of particles. Okay, kinetic energy average is equal to KE equals 1/2 mass times the speed, root mean squared speed. Root mean, yes, squared. Where m is the molar mass, expressed in units of kilograms per mole. The KE average of a mole of gas molecules is also directly proportional to the temperature of the gas and may be described by the following equation. Let me erase all this. Okay. Where R is the ideal gas constant. We'll go shut that door. And T is the temperature in Kelvin. Okay. When used in this equation, the appropriate form of the ideal gas constant is 8.314 joules per mole degree Kelvin. These two separate equations for kinetic energy average may be combined and rearranged to yield a relation between molecular speed and temperature. Okay, so we've got the two here. All this was to get to this, so we can do a math problem. Our molar mass times our average rate of speed squared equals 3/2 RT, right? Because we just substitute out our average kinetic energy. Right, and now what are we doing with this? We're going to solve for temperature, right? Or for average molecular speed. And so we get this, we get URMS equals the square root of 3RT over molar mass. Calculate the root mean squared speed for a nitrogen molecule at 30 degrees centigrade. So we're going to try to find that for nitrogen at 30 degrees centigrade. Go over here, I'm going to erase. Okay, so molar mass for nitrogen gas, 28 point what?
28.014.
Okay. Alright, so it should be about it, right? This is grams per, no, is that grams per mole? We probably need this in kilograms, right?
Yeah.
So I need to divide that by 1,000, right? So 0.028, 0.01, does that seem about right? Yeah. Okay, let's see. Yeah. Okay. Good. Okay. So did you do the math on it already? Me either. Let's do it. Okay, my calculator. What'd you get?
164.3.
That is not the right answer.
Might be the way that I rounded up. Maybe
What did you get?
164.3.
Well, I don't know, but it's just gonna be a calculator thing, because this is so simple, it's not like we can make many mistakes. You know, this times this times this, divided by that, square rooted. Or in my calculator, you have to hit your square root first, enter all that, close your parentheses, hit equals, and you get 519.56, which is the answer that the book likes.
It might be my calculator, because I'm using the phone.
Okay. Yeah, it's, at least we're confident it's only going to be a calculator, because we've got a formula set up right. Let's do one more, just for practice. Let's make sure we have a good time for this. As I said, around about 30 minutes. How many more problems do we have? Let's go quick. That's all I can say. Calculate the root mean squared speed for a mole of oxygen molecules at negative 23 degrees centigrade. Okay, so find RMS for 1 mole of O2 at negative 23 degrees centigrade. So RMS equals, I need 3 times, which constant am I using?
8.314.
8.314 joules per mole, degree Kelvin, right, times my temperature of, so it's going to be, what, 250 degrees Kelvin, right, over 16.02 divided by 1,000, so 0.0. Oh, no, I'm sorry, it's 13.04, is that going to be right? Or, sorry, 32.04?
Yeah.
32.04, it's kilograms per mole, all right.
And
So,
it's 250.15 Kelvin.
thank you, 250.15. Okay, very good. Got it going a little fast. So for mine, square root of 3 times 8.314 times 250 divided by 0.03204, close parens, should be 441, yes. Sure you got a good calculator for your test. Don't miss this, get that. Right? Of course, show your work. In case you do miss it, I can give you credit for the work.
Yeah, got the same.
Yeah. All right. The temperature of a gas increases, its kinetic energy average increases. More molecules have higher speeds and fewer molecules have lower speeds. The distribution shifts towards the higher speeds overall, that is, to the right. What do you don't need that. Next step. According to Graham's law, the molecules of a gas are in we're gonna stop there. I don't think you're gonna need this last bit. Okay. So you and I, no class next class. I think I was planning on not being here, but they asked me to preach chapel. They think, they're gonna let me know. But I'm planning on being here to preach chapel, but we'll still not have class. So test will be, online. I won't give anything over this last little section, the very last one. I don't think you're gonna need it anyways. And then I will see you at a test match. And after that, ideally, hopefully, Lord willing, intend to. And then after that, after spring break. So that's all I got. You have anything for me?
No.
Okay. Let's do this.